Yeah.
Michael, I guess it's time. We should start
Yes, we
now.
should be.
Yes.
Just a short introduction for Leron.
Sure. Let me shut up and let you carry on.
Okay, great. Good evening. Good to have you all with us. It's really a pleasure for me to introduce Leron Borsten, who will give the sixth OSMU lecture for this year on gravity as the square of Young-Mills theory. So Leron obtained his PhD from Imperial in 2010 under the supervision of Mike Duff, and his thesis was on aspects of M theory and quantum information. Since then, he has worked at various universities, including University of Turin, Dublin Institute of Advanced Studies, Imperial, Maxwell Institute of Mathematical Sciences, Edinburgh, and currently is a senior lecturer at the University of Hertfordshire. Leron's research interests are very broad and include quantum field theory, quantum gravity, supergravity, string theory and M theory, higher symmetries, homotopy algebras, scattering amplitudes, black holes, quantum entanglement in information, quantum measurement and causality, and causal set theory. He's made important contributions, including the Young-Mills origin of gravitational symmetries, 4-qubit entanglement from string theory, and black hole qubits and octonions. His other very interesting papers include the magic square from squaring of Young-Mills, the octonionic formulation of the M theory algebra, color kinematics, duality, and double copy. And as we know, for several years now, Leron has been thinking deeply about the relation between Young-Mills and gravity, and really looking forward to hearing from you, Leron. Over to you. We forgot to share your slides, but we can do it now.
Well, thank you. Whilst I'm sharing my slides, let me say thank you for that very generous introduction. And
you may need to share your screen, Leron.
Yes, sorry, I was struggling to do that. It seems to be working.
That's okay. We're fine. Yeah. We're home.
And hopefully you can see the full screen version now.
Yes, it's good. It's good.
Okay. So yeah, many thanks for the opportunity to tell you a little bit about gravity and Young-Mills theory. As you can see from my title, I've elaborated a little to include the words homotopy algebras, scattering amplitudes, and color kinematics duality. And I've probably been a little ambitious in trying to tell you all of these things in one go, but I can stop at any point. I don't have to tell the complete story in the hour. There are many good places to kind of cut it short. So we'll see where we get to, and please stop me with questions along the way. I don't want this to be hurried. This has been work done with lots of collaborators, including Alessio Marrani, who's in the audience right now, and my PhD supervisor, Michael Duff, and more recently, collaborators spread across the UK and Europe, such as Christian Saemann and Martin Wolf, and Brano Jurco in the Czech Republic. Okay. So this is really a talk of two themes that I want to bring together. And the first theme, which I assume possibly people are less familiar with, is the relationship between perturbative quantum field theory and what we call homotopy algebras. And there's a basic dictionary that relates these two subjects. So on the one hand, in perturbative quantum field theory, one might start with the classical Batlan-Vilkovsky action, S, and begin that as your starting point of quantizing and constructing scattering amplitudes. And it turns out that this BV action, S, corresponds precisely to what's called a cyclic L-infinity algebra, which I'll denote L for L-infinity, and with a little S to remind us that it's associated to this quantum field theory. And in particular, the scattering amplitudes of S correspond to what's known as the minimal model for this L-infinity algebra. And various other features fit into this. So often we have to choose a gauge when we have some gauge theory. And this corresponds to an embedding of this minimal model into the full L-infinity algebra. I'll come on to describe what the right-hand side means in more detail later, so don't worry if these are just vague words for now. And then this gets enriched. So for instance, we can consider integrating out fields in a kind of Wilsonian sense for our quantum field theory. And this corresponds very precisely to the notion of what's called homotopy transfer of L-infinity algebras. We can often have two inequivalent actions that capture the same physics, so S and S tilde, and this corresponds to what are known as quasi-isomorphisms of these L-infinity algebras. The Feynman diagrammatic expansion of scattering amplitudes is captured really neatly by something known as the homological perturbation lemma. And various properties of scattering amplitudes, such as recursion relations, are encoded in this homological perturbation lemma. And when the amplitudes of a particular theory have some special properties, we can often translate those into some algebraic refinement of the corresponding L-infinity algebra. So to give you some sense of what I mean by this, let me give you the very simplest example of this notion. So if you have a Yang-Mills gauge theory with some color Lie algebra, you can consider the color stripped amplitudes, where you separate out the color data of the amplitude and you're just left with the bare kinematics, the momentum polarization of the gluons. And this corresponds very concretely to the fact that this L-infinity algebra factorizes into a tensor product where one factor is the color Lie algebra G, and the other factor is now not an L-infinity algebra, but what we'd call a C-infinity algebra. So L-infinity, the L there is meant to be capturing the notion of a Lie. It's a homotopy Lie algebra. The C here is a graded commutative. So this is a homotopy graded commutative algebra. And this kind of enrichment of the algebraic structure of the underlying L-infinity algebra, the enrichment I want to tell you about is related to something known as colour-kinematics duality. So certain quantum field theories enjoy their scattering amplitudes enjoy a property called colour-kinematics duality. And this corresponds in a very precise sense to the fact that the associated C-infinity algebra, this thing that you have once you've stripped away the color, is what's called a homotopy BV box algebra. Okay, these are all just terms. I'll explain what they are later. And then something known as the double copy rather straightforwardly corresponds to the tensor product of these BV box algebras. Okay, so at this stage, you may or may not know what colour-kinematics duality is and what the double copy is. And that takes us on to the second theme of this talk. So theme 2, broadly speaking, is the idea that in some sense, gravity can be understood or reconstrued in certain limits as the double copy of Yang-Mills gauge theory, as depicted in this cartoon equation here. You can imagine the metric characterizing space-time as being, roughly speaking, the tensor product of a left gauge field with a right gauge field. And you might be wondering, you see you've got the appropriate Lorentz indices sitting here, but you might be wondering what happens to these color indices sitting up here. And that's where this story of color kinematics duality enters. So this idea of gravity as somehow being the double copy of the fundamental forces of other fundamental forces of nature is quite an old idea, going back at least to Richard Feynman. But it's undergone a relatively recent renaissance, driven by what's known as the Bern-Carrasco-Johansson color kinematics duality conjecture and double copy of gauge theory and gravity scattering amplitudes. So that's broadly speaking what the second theme is about. And because I've probably presented too much material, I thought I'd start by giving you the punchlines, so that if we don't get right to the end, you still have the goal in sight. So punchline number 1 is that this color kinematics duality is at first sight a mysterious property of scattering amplitudes, which roughly says that the kinematic properties of the scattering amplitudes, the kinematic data of the scattering amplitudes, that is the momenta and polarization tensors of the incoming and outgoing, let's say, gluons, obey the same, there is a realization of the amplitude in which they obey the same algebraic properties as the color data of the amplitude, which is controlled by the Lie algebra gauge group. Okay. And punchline number one is that this mysterious property of scattering amplitudes can be translated into a conventional symmetry of the BV action for the corresponding theory with a kinematic Lie algebra associated to it. Because the kinematic data obeys the same algebraic relations as the color data, and the color data belongs to a Lie algebra, it's natural to suspect that there might be some kinematic Lie algebra hiding there. And indeed there is. There's an important caveat here. I've put the words possibly anomalous. So you can make this color kinematics duality of the scattering amplitudes a symmetry of the action, but it may be anomalous in the sense that counter terms that enter at the loop level to make unitarity manifest break this color kinematics duality symmetry. I'll explain that in more detail later. So that's punchline number one. We turn this mysterious property of color kinematics duality into a conventional symmetry of the action. Now, assuming color kinematics duality of we can double copy scattering amplitudes. And what do I mean by this? I mean this is a prior fact. This isn't my punchline. This is a known fact from the literature. If I've got color kinematics duality, I can take a pair of gauge theory scattering amplitudes and generate from them a gravitational scattering amplitude for free. This is reflected in the fact that there is an action double copy. There's a double copy at the level of the action, not just at the scattering amplitudes, that corresponds to the tensor product of these underlying BV box algebras that gives us a gravitational L-infinity algebra. Okay, and some corollaries of this. Well, one thing that's nice is once you know this, you can start finding out whether a theory has quantum color kinematics duality by looking at the action itself rather than the scattering amplitude. So for instance, one can prove that self-dual super-Yang-Mills theory in 4 dimensions has perfect off-shell color kinematics duality. And we do this, interestingly, using twistor space. So I'll come on to describe how twistor space enters this story towards the end of the talk. And there are various other generalizations that come for free, essentially. So for instance, you might consider the M2 brane world volume theories, and we can show that these have tree-level color kinematics duality using these ideas. Okay. So the plan for today is to begin with a review of homotopy algebras and their relationship to quantum field theory and scattering amplitudes. In particular, I want to discuss how L-infinity algebras get connected to the BV formalism, and then how this connects you to scattering amplitudes. I'll then have a change of pace, talk about color kinematics duality in the double copy, and this property that gravity equals gauge theory times gauge theory. And then I'll bring these two ideas together in the final 2 parts. So first of all, I'll tell you how to manifest color kinematics duality in the BV formalism. And then I will tell you how this translates into the homotopy algebraic picture developed in the first part of the talk. And we'll end with some examples that illustrate all of these principles at work. So in particular, we'll look at Chern-Simons theory and self-dual super-Yang-Mills theory. Okay, so homotopy algebras, quantum field theory, and scattering amplitudes. And let me emphasize, please stop and ask questions. I'm really happy to take questions throughout the talk.
So just a small, quick question. So how do you define gravity in this context? The action is made from the Riemann tensor. Is that the definition of gravity?
Yes. So when I'm talking about gravity here, I haven't been very careful. But what you get from pure Yang-Mills, when I talk about double copying pure Yang-Mills to gravity, what one gets is Einstein-Hilbert gravity coupled to a pair of scalar fields, if we're in 4 dimensions, the axion and dilaton, that appear in string theory. So I'm not getting pure gravity. There are some tricks one can play to get pure gravity developed by Henrik Johansson and Alexander Ocharov, but I won't describe them. And then those kinds of manipulations where you truncate away the extra scalar fields that one is automatically getting out of this construction to get pure Einstein-Hilbert gravity, i.e. the action is rarely just root det g times the Ricci scalar. Those kind of tricks are not going to be a part of my talk, but we can discuss them afterwards, certainly.
Thank you. Thank you.
Okay, so to begin with, let me try and motivate what a homotopy algebra is. And I want to start with a cochain complex. So by a cochain complex, I mean a graded vector space. So that means a direct sum of vector spaces that carry some degree. I've called them Ci here. I is the degree of this component of the vector space, and some map between them, the differential, that carries degree 1. So it shifts you up a degree. And being a differential means that it squares to 0. And I'm going to assume that on top of this cochain complex structure, there is some compatible algebraic structure, i.e. some kind of multiplication map, M, that takes two elements in this graded vector space and spits out an element in the graded vector space in such a way that the degrees add up in this way. So it's a degree 0 multiplication map. And what do I mean by this algebraic structure being compatible with the differential? Well, I just mean that the differential obeys the Leibniz rule with respect to whatever this multiplication map is. So here's the graded Leibniz rule written out here. I have the grading because I've got a graded vector space. And the canonical example, which I hopefully will orientate you all, is the Hodge-Durand complex of I-forms, P-forms, I-forms just to be consistent with my notation up here, over some manifold M, where the differential is really just the usual exterior derivative. And then the multiplication map, as you might imagine, is just the wedge product amongst I-forms. So as we all know, the differential, the exterior derivative really does behave as a graded derivation with respect to the wedge product. So we satisfy this condition here. In fact, the wedge product has a little more structure. It's graded commutative in this sense. So this gives us a differential graded commutative algebra, or a DGCA for short, but a graded differential commutative algebra. Okay, so that's the key example one ought to have in mind. Then we could ask a question. Given two cochain complexes, so I've got my original guy up here, which remember has some algebraic structure, this multiplication map, and a chain morphism, that is a family of maps phi I, such that all of these squares commute to some other cochain complex with another differential. We could ask the question, can the algebraic structure M on the upper complex be transferred to an algebraic structure M tilde on the lower complex? Now, if you're being completely strict about this, generically no, the answer is no. Some of the properties that you have for this M may fail if you just naively pass through these maps. But the answer is yes, if we allow for a richer homotopy algebraic structure. So the idea is that the algebraic identities of whatever this product are, in our case, it was graded commutativity, but you could consider associativity or the Jacobi identity or whatever algebraic properties you have in mind, only hold up to cochain homotopies, which are given by higher products on the chain complex itself. So now, in addition to the differential, which I will now call M1, and the multiplication map, which I will now call M2, we can have higher products, M3, M4, M5, which take 3, 4, 5 arguments each and spit out something in some higher degree component of the chain complex. So informally, what's going on here is that we generalize familiar algebras to include higher products satisfying higher relations, for instance, graded commutativity, up to homotopies. And you can play this game for all sorts of algebras, and the three key examples that I have in mind are associative algebras, and their homotopy relaxation in this sense that I've just described are known as A-infinity algebras or homotopy associative algebras. Commutative algebras predictably give you homotopy commutative or C-infinity algebras. And the key example for us, Lie algebras generalize to homotopy Lie algebras or L-infinity algebras. And I should mention, in the physics literature, these were discovered by Bartens Rieback in the context of closed string field theory, but also independently discovered in the maths literature, applying the ideas of Jim Stasheff to Lie algebras, essentially. Okay, so what is a homotopy Lie algebra, more precisely? Well, it's probably easiest just to compare with a Lie algebra. Recall a Lie algebra is a vector space, which carries no grading, equipped with a Lie bracket, i.e. a 2 product, which I will call mu2, that obeys some relations. In particular, the Lie bracket is antisymmetric and obeys the Jacobi identity. So its homotopy generalization, or an L-infinity algebra, is a graded vector space. So it's a direct sum of vector spaces that carry some degree. And now, rather than just having the Lie bracket, we can have a unary bracket that takes 1 argument, a ternary bracket that takes 3 arguments, and so on and so forth. Now, these obey a graded antisymmetry identity on the nodes, but the Jacobi identity is relaxed up to a homotopy. And the homotopy will be given by these higher products. So let me give you a concrete example, known as a semi-strict Lie2 algebra. Now, a semi-strict Lie2 algebra you can arrive at as through the theory of Lie2 groups, but it also coincides precisely with what's called a 2-term L-infinity algebra. 2-term in the sense that the graded vector space only has 2 components, and in my conventions I'll take them to be v-1 and v0, but it can, and in this case there are 3 brackets. Mu k is non-trivial for 1, 2, and 3, for k equals 1, 2, and 3, where mu1 is the differential, mu2 is the Lie bracket, and mu3 goes by the name of the Jacobiator. And you see here, I have the graded Jacobi identity, but it doesn't hold on the nodes, it doesn't equal 0. Instead, it equals the unary bracket, i.e. the differential, acting on the ternary bracket. So if the ternary bracket was 0, it was identically 0, we'd have an honest-to-goodness graded Lie algebra. But when the ternary bracket is non-trivial, we only get the Jacobi identity up to this homotopy term. So that's the first kind of example that has some non-trivial generalization. Okay, so that's roughly speaking what an L-infinity algebra is. But to be able to do something, I need to know what these homotopy Jacobi relations are. How did I know that this is what appears on the right-hand side? Well, there's a very general mathematical framework for this. I think it was Bruno Valette who coined this term, that if you take algebra and homotopy, you get something called operads. And these operads give you a very powerful general mathematical framework for generating these homotopy algebras. And essentially, you can think of an operad as the abstraction of what it means to have an operation that has many inputs. This definition isn't very illuminating in terms of operads if you actually want to do calculations. If you want to do calculations, it's much more helpful to unpack this. And then you get that an L-infinity algebra, more precisely, is a graded vector space together with graded antisymmetric I-linear maps, these mu i's, of degree 2 minus I, that satisfy the homotopy Jacobi identities. So this formula here gathers all of the homotopy Jacobi identities for all of these multilinear maps together into one expression. Importantly, you see that it's just quadratic in the maps. So it really is like a Jacobi identity. The Jacobi identity it only involves pairs of Lie brackets. Here we just have pairs of higher brackets. Unpacking the first few of these, we see that they're quite simple. So for instance, at the very lowest order, we learn that the homotopy Jacobi identities enforce the fact that mu1 really is a differential, i.e. it squares to 0. It also enforces the fact that mu1 is a graded derivation with respect to mu2, just as we had before. So you see that the mu1 passes through the mu2 like a derivative. And this final expression that I've spelled out is on the left-hand side, the graded Jacobi identity. And you see here on the right-hand side, it fails up to terms involving mu1 and mu3. And you could unpack, if you wanted, all of the higher Jacobi identities. Okay, so this mu3, importantly, is encoding the failure of the Jacobi identity up to homotopy. Okay, so that's roughly speaking, or quite precisely speaking, what a homotopy Lie algebra is. And the first important concept that one needs to capture is the notion of morphisms, maps between L-infinity algebras, generalizing the notion of homomorphisms between Lie algebras. So a morphism of an L-infinity algebra, well, they're families of I-linear maps. So they take I arguments, spit out something in the new L-infinity algebra that are functorial in the appropriate sense. That is, there are some coherence relations obeyed with the obeyed by these maps with respect to the products. And in particular, at the lowest order, we learn that these morphisms are chain maps in the sense that they commute with the differential. The fact that the lowest member of this family of maps is a chain map, means that we can restrict to the cohomology, the mu1 cohomology of the underlying cochain complex. And that gives us the notion of a quasi-isomorphism. These are morphisms that induce isomorphisms on the mu1 cohomologies. So we've got an isomorphism amongst the cohomologies as determined by this differential. Okay. Now, given this notion of quasi-isomorphisms, we have two very powerful theorems that we're going to want to use. The first one is known as the strictification or rectification theorem. It says that every L-infinity algebra is quasi-isomorphic to some other L-infinity algebra. I've put a little tilde on it here, where all of the higher maps are identically zero if I is greater than 2. We call it a strict L-infinity algebra. So it's essentially a graded differential Lie algebra in this case. It's only got a differential and a Lie bracket. The second important theorem, which has a little more richness to it, is the minimal model theorem. This says instead that every L-infinity algebra is quasi-isomorphic to another L-infinity algebra that has as its underlying graded vector space the cohomology with respect to the mu1, with respect to the differential. And because this is on the cohomology, it means that the differential in this minimal model is identically zero. Now, this minimal model theorem, there's a kind of canonical way of constructing what we call the minimal model, this guy over here, through what are known as special deformation retractive complexes. So for the moment, if I just forget about all of the higher product structure on this L-infinity algebra and just consider only the graded vector space and the differential mu1 and throw away all of the other higher products, then I can project to the cohomology here, and I can also embed the cohomology back in the original vector space. And these projections and embeddings give you the identity operator. So I can first project and then embed, and I get the identity up to a contracting homotopy H. That's what these terms here are. So I get these extra terms. So if I project and then embed, I don't have the identity, but I can always correct for it with some contracting homotopy over here, which is some degree -1 map on the original cochain complex. And then I can run something known as the homological perturbation lemma, which says I can deform this cochain map with this homotopy to include the higher products and recursively build up the higher products of the minimal model. So, for instance, the differential is 0, as I stated, and then the Lie bracket, the binary product, you just embed the minimal model in the full model, use the bracket of the full model, and then project back down to the minimal model. And then if you wanted to construct the cubic map, the ternary map, well, first of all, you can embed all of the arguments from the minimal model into the full model, use the ternary product of the full model, and then project down to the cohomology, project back down to the minimal model. But you could have also embedded one argument here, embedded these two arguments here, and then put them into the Lie bracket, the binary product of the full model, apply the contracting homotopy. I'm missing a projector here. There needs to be a projector back. Oh, no, sorry, that's correct. And then apply the Lie bracket of the full model and then project back down. And just to build up the anticipation, this is really a Feynman diagram construction going on here. This is how we're going to get to scattering amplitudes. But I'll spell that out more clearly in a moment. Okay, so that was the minimal model theorem. Now, given a differential graded Lie algebra with a cyclic inner product, so what I mean is some kind of metric that ablaze, which I'm denoting by these angle brackets, a metric on the vector space, that obeys this cyclic property, which is just the property generalizing the cyclic property of the Cartan killing form. We can define Maurer-Cartan elements and actions, i.e. a Maurer-Cartan element is some element in the graded vector space that satisfies this equation, i.e. the field strength is flat. And I can also write down a Maurer-Cartan action where this equation, the fact that I get a flat field strength, is really just comes from the variation of this action. This is like Chern-Simons theory. And then I've got a corresponding notion of a covariant derivative, Bianchi identities, and gauge transformations, which should hopefully look familiar from standard Chern-Simons gauge theory. Taking all of these words, I can now immediately generalize to the case of L-infinity algebras, where rather than having just a standard inner product with the standard cyclic structure here, I generalize this in the obvious way, where I now have cyclicity for all of the higher products. And we could define a homotopy Maurer-Cartan elements and actions in exactly the same way. So you see here, this is mu1 plus a half mu2. And then you can imagine, well, what do you do if you have mu3? Well, you take 1 over 3 factorial mu3 plus 1 over 4 factorial mu4 and so on. That's just what I have here. It's what I mean by a Maurer-Cartan element. And then I've also got the analogously obvious homotopy Maurer-Cartan action. And this field equation here corresponds to the variation of this under the assumption that cyclicity is obeyed here. Okay. And we also have covariant derivatives, Bianchi identities, and gauge transformations. And you can maybe get a sense of how this gives us the notion of higher or homotopy gauge theories. Okay, so now the punchline of this is that every Batlan-Vilkovsky-Lagrangian field theory corresponds directly to a cyclic L-infinity algebra. So to make this concrete, let me consider Yang-Mills theory, the Batlan-Vilkovsky theory of Yang-Mills. Well, here I've got the Yang-Mills gauge potential. It's just a Lie algebra valued 1 form. I've got its corresponding anti-field, which is also a Lie algebra valued 2 form now. I've got the gauge ghost corresponding to the gauge symmetry, which is a 0 form, and its dual anti-field anti-ghost, which is a 3 form. So this will now be my underlying graded vector space. It's basically forms valued in the color Lie algebra. And I can write down the homotopy Maurer-Cartan action for a superfield, i.e. some inhomogeneous combination of the ghosts, the physical Yang-Mills gauge potential, and the anti-fields. And then the homotopy Maurer-Cartan action really is just the BV action for Yang-Mills, where, for example, this cyclic structure is the trace of the integral over the top form given by wedging the fields with antifields. And mu1 in this case is just d star dA. So you can see here that if I plug this to the homotopy-Marrani action, I get this first kinetic term here. I get A wedge star d dagger dA. And you'll realize that mu1 acting on A really is just the Maxwell equation. This is the Maxwell equation. And what's important here is that this means that the cohomology, this cohomology that I've been talking about that appears in the minimal model, is really just the degree 1 component of the cohomology. It's the space of on-shell physical states. They are the transverse photons in this case, or the transverse on-shell gluons in the case of Yang-Mills. And I can color strip by factoring out the color Lie algebra, and that gives me this Yang-Mills C-infinity algebra. Okay, so that's how we relate homotopy Lie algebras to the Batman-Vilkovsky approach to quantizing gauge theories in a nutshell. Now we can go back to this minimal model and recall. So I've got some graded vector space corresponding to my BV theory. I've got some products that encode the BV action. And I've got this minimal model theorem that says it's quasi-isomorphic to its cohomology with respect to mu1. And recall that mu1 is the differential that encodes the kinetic term, encodes the free linear equations of motion. So this cohomology is the space of on-shell states. And then the minimal model theorem and the homological perturbation lemma corresponds to constructing the scattering amplitudes. And in particular, we see that H is inverting the differential operator defining the linearized equation of motion up to this projector here. So it really is a propagator in a traditional sense, that it inverts the differential operator, the kinetic differential operator, away from the cohomology. So it gives you the identity away from the cohomology. And if you run this homological perturbation lemma, you really discover the higher brackets of the minimal model in terms of a Feynman diagrammatic expansion. So here I've just repeated those equations that I had before, and I've put them in a Feynman diagrammatic form. So here is the Lie bracket of the minimal model. And you see what I'm doing is I embed the on-shell states, these V tildes, into the full theory. That's like embedding gluons into the full space of the Yang-Mills gauge field. Then I apply the vertex of the binary vertex of Yang-Mills gauge theory, and then I project back on to the on-shell states. And basically, this is giving me the 3-point amplitude. And if I take the 3 brackets, I see I have this 4-point vertex here, and then I've got this 2-point vertex appearing here, and this H sitting here appears as the propagator in this Feynman diagrammatic expansion. So you really just get a Feynman diagrammatic reconstruction of the minimal model from the full theory using this contracting homotopy. And then we get that the generating functional of the tree-level S matrix, or the tree-level scattering amplitudes, really is just the cyclic L-infinity algebra given by the minimal model. And the punchline of this is that actions and amplitudes are unified as quasi-isomorphic L-infinity algebras. They really are the same mathematical objects in this sense. The only real distinction is that in a certain sense, the minimal model is canonical. It's kind of unique. And you can imagine that because there are many off-shell realizations of the same on-shell data. Okay, so I'm probably taking up too much time telling you about homotopy algebras and scattering amplitudes. So let me move on to theme 2, color kinematics duality and the double copy. So here, to set this up, I want to just schematically draw out what a gluon scattering amplitude looks like. So here I'm considering for n external particles and L loops, and I can massage it. I can always rewrite it as a sum over cubic Feynman diagrams. That's where I only have trivalent vertices, of integrals over the loop variables, of integrands, and now it's the integrands that I'm really going to be interested in here, that have three pieces. They've got the propagators, which is a kind of a universal piece. And then they have a kinematic factor, which we call the kinematic numerators, that are built entirely out of the kinematic data. That is the polarization tensors and momenta of the external gluons. And then the color numerators, which are built entirely out of the Lie algebra structure constants of the corresponding color gauge group. And what color kinematics duality states is that whenever a triple of these color numerators obeys a Jacobi identity, which is their raison d'etre, they do this all of the time. Well, in many instances, you can take triples of diagrams, you can find those where the color factors sum to zero because of the Jacobi identity. It implies that the kinematic numerators obey precisely the same identities. This is actually a highly non-trivial observation. It's been proven at tree level from many different perspectives, but it remains conjectural at loop level, although there are highly non-trivial examples. So this is some kind of fascinating relationship between the color components and the kinematic components of a gluon scattering amplitude. So just to give you some illustration of what's going on here, what I really mean by this, let me do the simplest non-trivial example. That is the 4-point scattering amplitude at tree level for gluons. So here I've written the usual S, T, and U channel diagrams for gluon scattering. And I've written out what their corresponding contributions to the amplitudes are. And you see they each have a Lie algebra part and a kinematic part. And I've called each Lie algebra part C, S, T, and U for those particular channels. And then the corresponding kinematic part, NT, NS, NT, and NU. And then there's this 4-point guy, which lands up having the same color components with some distinct kinematic components. Okay. Now, what I can do, I started out saying that we can write the amplitude as a sum of purely cubic diagrams. And here I've got this 4-point interaction spoiling that picture, but I can distribute it amongst the ST and U channels. So I can take this 4-point diagram and I can divide and times by a propagator, S, T, and U here. And in that way, distribute it amongst the S, T, and U channels in this way, so that I get new kinematic numerators. Let me put little tildes on them to distinguish them from the original guys, where I've got this little Mandelstam variable sitting in each one. I haven't changed the amplitude at all. I've just absorbed the 4-point amplitude in the 4-point contribution into the 3-point contributions. And then I can write the amplitude in this form, now purely in terms of trivalent diagrams, where I've got these new kinematic numerators. And by the Jacobi identity, I have that CS minus CT minus CU equals 0. And it's a straightforward exercise that's been known for a long time now, that NS tilde minus NT tilde minus NU tilde also equals 0. We see that the kinematics appears to be playing by the same rules as the color. And as I mentioned, this kind of semi-trivial example can be generalized to all points at tree level, and you can show that it works for limited loop numbers, but the general loop statement remains a conjecture that I will come back to later. Okay, very good. At this point, you might be wondering, what does color kinematics duality have to do with gravity? Why should I care about this? Well, let's first motivate this by comparing the gluon 3-point vertex. Here it is. It fits in one line. And writing out, courtesy of John Joseph Carrasco, the corresponding graviton 3-point vertex. It's this big mess here. But if I actually compute the 3-point amplitude for the graviton, I land up with this extremely neat expression. That big mess gets contracted down to this single line, which turns out to be precisely the square of the 3-point gluon amplitude. And of course, here I'm considering complex momenta so that I get something that's non-zero. So this is interesting. I see a graviton amplitude being the literal square of a gluon amplitude, and you might wonder if this generalizes. And indeed it does. This is where the double copy and color kinematics duality comes in. Assuming color kinematics duality is realized in your scattering amplitudes, then gravity comes for free. What do I mean? Well, I take my gluon amplitudes, I take the color factor here, I replace it with a second copy of kinematics. That's what I mean by the double copy. And what it produces is a genuine gravitational amplitude, i.e. this is some amplitude for gravitons. And because I've got the axion and dilaton floating around, I might have these two scalars being included. Okay, so that's what I meant by the double copy. Given color kinematics duality, you can get gravity for free from Yang-Mills with no extra data being put in. Now, the question is, can you make this property of the scattering amplitudes somehow manifest in the initial Lagrangian starting point? And the answer is that we can do this using the BV formalism, up to some caveats about counter terms that I'll come to later. So the first important observation is that you can manipulate the action for Yang-Mills theory so that the Feynman rules it generates automatically give you color kinematic dual, tree level, physical S matrix scattering amplitudes. The way this works, I've got Yang-Mills written out schematically here. This is this box over box in front of this quartic term. It's just this method realized at the level of the action of absorbing the 4-point contact term into the 3-point diagrams. And I can add a quintic term that repairs for the failure of the color kinematics duality to work. And this quintic term is identically equal to 0 due to the color Jacobi identity. So I'm really just adding 0 to the action. So clearly this is an equivalent action because I'm adding something that is identically 0, but it's identically 0 in such a way that its contribution, this 5-point contribution, distributes into the 3-point diagrams so that each kinematic numerator individually of these 3-point diagrams satisfies color kinematics duality. That gives you tree level physical S matrix color kinematics duality, but it doesn't give it to you for loops or anything off shell. And we can use this strictification theorem to show that we can reduce this quintic term down to purely cubic things by introducing some auxiliary fields. So I've got an auxiliary B field here and some auxiliary C fields, and I get a purely cubic theory that has automatically color kinematic duality satisfying Feynman diagrams. Now, to lift this to loop level, we should really include off-shell, unphysical, longitudinal ghost modes in the external state, so we can glue these trees together into loops. To do this, we really want to lift the idea of color kinematics duality to the full off-shell BRST extended Hilbert space. Okay, so to begin with, we might consider relaxing the transversality of our external states. So here I want to consider longitudinal gluons. What we find is that color kinematics duality fails. It gets broken by the longitudinal modes. But we can always compensate these failures with new vertices introduced to the action that are pure gauge, i.e. we can make a gauge choice that compensates for these failures. And here's an example of such a gauge choice with the corresponding ghost terms. The details are not important, just to say that you can rarely do this in concrete terms and find Feynman rules that satisfy color kinematics duality for on-shell physical gluons, but also for longitudinal gluons and their corresponding ghost states. And the proof is inductive and constructive. I won't take you through it. We can come back to that if you're interested in the details. And then finally, this was for on-shell modes. So I've got on-shell longitudinal modes, on-shell transverse modes, and on-shell ghosts. And really, if we want to glue these trees into loops, we have to lift the off-shell momenta. And again, having off-shell momenta will generically generate CK duality violations, but we can also compensate these by vertices. And this will yield cubic Feynman rules that give you perfect color kinematics duality for loop integrands automatically, with a very important caveat. Because these transformations may generically be non-local, we may recover Jacobian determinants that do not vanish under dimensional regularization, so they produce counterterms required to ensure unitarity. And there is no reason to think that these such counterterms will preserve CK duality. So in this sense, although the Feynman rules prior to introducing the counterterms have manifest CK duality, it may be anomalous. It gets broken by the counterterms required for unitarity. And this is really consistent with the empirical results from the literature. So for instance, two-loop color kinematics duality with a local Lorentz covariant cubic Feynman rules compatible numerators is impossible. So we now understand this impossibility as a color kinematics duality anomaly. All right, so let's summarize everything we've done. Color kinematics duality can be realized and as an infinite dimensional, possibly anomalous symmetry of the Yang-Mills BRST action. And schematically, what one lands up with is an action of this form. We've got some Yang-Mills gauge fields that have some color indices and some kinematic indices. And we have the usual color structure constants together with some kinematic structure constants, which are differential operators, multilinear differential operators. And importantly, they satisfy exactly the same identities. So you rarely see that the color is mirrored precisely by the kinematics. They obey the same kinematic identities. So we see that color kinematics duality is a symmetry of the action in the same way as the gauge symmetry, the color gauge symmetry, was a symmetry of the action. And these structure constants are the constants of some kinematic Lie algebra. And the loop integrands that you get from the Feynman rules are perfectly color kinematic dual, but there may be color kinematics duality anomaly due to the Jacobian counterterms. Okay, that's the kind of summary. And I should emphasize, in this construction, we had to introduce at each order new sets of auxiliary fields. So this index I is like a multi-Lorentz index that's really labeling an infinite tower of auxiliary fields. And once we have this, the double copy becomes almost child's play. You take your color kinematics dual representation of the action, and wherever you see a color thing, you replace it with the corresponding kinematic thing. So the red C's and F's go to new copies of the blue C's and F's. And it really is like you take two parent Yang-Mills theory, you separate out their color and kinematics, and then you marry the kinematics together. And the first term you get for pure Yang-Mills is really just the Einstein-Hilbert action. And these ellipses are hiding the axion-dilaton terms and whatever else you get given different input data. So we rarely see gravity appearing as the double copy in a very literal sense of Yang-Mills. Okay, very good. But there are some problems. First of all, our proof that went into these statements is constructive and inductive. So we built these terms order by order, and what we do is show that given the terms to one order, you could build them at the next order. So we know we can do this, but we didn't have any theoretical understanding or control of what these terms were, or what this infinite set of auxiliary fields is. No theoretical control. And correspondingly, there was no closed form for the color kinematics duality manifesting action. We just had to build it order by order. And we had no clue generically about what this kinematic Lie algebra is, because we had to develop it order by order. Finally, there was this possible need for non-local field redefinitions, which could lead to color kinematics duality anomalies. And we had this nice, simple picture of what it meant to double copy at the level of the actions, but mathematically, it's a little opaque. We expect it to correspond to some tensor product, but what is it mathematically? So we'd like a clear mathematical characterization of the higher vertices. We'd like a closed form for the color kinematics duality manifesting action. And we'd like to avoid the need for non-local field redefinitions. And really, we'd like to understand the kinematic Lie algebra and the tensor product of the C infinity algebras that generate the double copy. So this is what the final part is about. I know I only have 4 minutes, so maybe I could just sketch the broad idea, and then we can carry on in the discussion and get into the details if people are interested. So one of the key insights came with the work of Michele Reiterer in 2018, who realized that you could prove color kinematics duality of the physical tree-level S matrix, that is, of the scattering amplitudes. You could prove this in terms of what is called a BV infinity box algebra, which is a deformation of the more famous BV infinity algebras that arise in topological vertex algebras. And what we realized is that the kinematic Lie algebra corresponds to a BV box algebra. And the fact that when you have color kinematics duality, that the C infinity algebra actually corresponds to a BV box infinity algebra. And these higher products that I've been talking about that we generated through this constructive inductive proof correspond to these higher products of the BV box infinity algebra correspond to these various things. So certain products correspond to the color strip gauge fixed action vertices and various other things. We gave the details of these. And perfect color kinematics duality corresponds to what we call a strict BV box algebra. So I've got some differential graded vector space with a differential and this multiplication map. But in addition, a degree -1 operator that squares to 0 and anti-commutes with the differential to give you a box. And really you should have in mind that this box is the Delin-Burschen, and it's second order with respect to this product, which means it doesn't behave as a derivation, but that the derived bracket behaves obeys the Jacobi identity. So we get a shifted Lie bracket, which is the kinematic Lie bracket. And roughly speaking, what's going on here is that the homotopy is provided by this B operator over the box, this homotopy that gives you the scattering amplitudes. And then you realize that you can put this, you can shift the B from the homotopy onto the products, and then you get kinematic, and you find that the products encoding the vertices automatically satisfy the Jacobi identity. And then we realized the double copy as a tensor product of these BV box infinity algebras in a precise mathematical sense. I won't go into the details. I can come back to this. So let me end, if you'll permit me to go 2 minutes over time, with the paradigmatic example of Chern-Simons theory.
Leron, you can take some time, no hurries.
Sure. Let me talk about Chern-Simons, then I'll stop, and then that leaves space to discuss other examples. Okay, so it was realized in 2021 that Chern-Simons theory, although it has no non-trivial amplitudes, being a topological theory, has perfect off-shell color kinematics duality. And seeing this, we realize that Chern-Simons must have a perfect BV box algebra structure. And indeed it does. It's very simple. So the underlying graded vector space is just P forms valued in the Lie algebra, where I've got the naught forms of the ghosts, the 1 forms are the Chern-Simons 1 form, 2 forms are the anti-fields, and 3 forms are the anti-field anti-ghosts. And the homotopy Marakatan action is just the BV action of Chern-Simons theory. And here, this B operator that I was talking about, this degree -1 differential, is incredibly simple. It's exactly what you'd expect it to be. It's just the adjoint to the exterior derivative. And of course, the adjoint to the exterior derivative anti-commutes with the exterior derivative to give you precisely the Delin-Burschen, where now the product is just the wedge product. So this BV box algebra couldn't be more straightforward in this case. It's just the Hodge-de-Ram complex with the wedge product plus the adjoint to the exterior derivative. And then the kinematic Lie algebra is given by this derived bracket, which long ago was already known to give you the Schotten-Nirenhausen algebra of totally anti-symmetric tensor fields. And then if we restrict these, restricting this kinematic Lie algebra to the physical fields, we get the diffeomorphisms, We just get straightforward diffeomorphisms. So here, everything becomes very clear. We get a very clear BV box algebra that tells us that we have color kinematics duality. The kinematic Lie algebra of the color kinematics duality is diffeomorphisms on the physical fields. It's slightly more general on the full space of the BV complex. And everything makes complete sense. And because the box here is precisely the D'Alembert, we get color kinematics duality on the nose to all points and all loops for off-shell currents. So there's a guiding principle here. Look for Chern-Simons type actions. So once we realize this, we realize we could play this game, for instance, with any theory that you could put in a Chern-Simons type form, and then your job is to find a B, the generalization of the adjoint to the exterior derivative. So just to give you one final example, we could take super self-dual Yang-Mills, which is quantum equivalent to holomorphic Chern-Simons theory on super twistor space. This is where the twistor theory enters. So the super is needed so that we don't have a twistorial anomaly, but at the tree level, we could just go to standard twistor space. And standard twistor space is diffeomorphic to R4 cross CP1. And then what this CP1 is doing, what you can think about it doing, you can think about Zoccali expanding over the CP1. So all of these fields here are fields that are valued on R4 cross CP1. Well, they're sections of bundles over R4 cross CP1. And you can imagine Zoccali expanding over this compact space to give you a Zoccali tower of fields. And that Zoccali tower of fields is precisely this infinite tower of auxiliary fields that we needed to enforce color kinematics duality. So we start understanding that there is this general principle for writing down closed form actions for color kinematics duality respecting actions. And then we get closed forms for their double copy, which gives us gravitational actions on the nose. Okay. There are more examples. I think I will pass over these. We can come back to them. And then just mention some future directions. So there's many ways you could take this. For one, we would like to have the analogous statement for Yang-Mills theory itself. I was just talking about self-dual Yang-Mills theory. Turns out that the generalization to Yang-Mills theory should pass through ambitwistor space, but the story is much more complicated there. And the proof that color kinematics duality really holds to all loops has resisted for various reasons. And we don't know if this means that color kinematics duality simply doesn't work for Yang-Mills theory, or that there are just some technical problems that we still have to resolve. And this remains an open question. Another obvious generalization, which is the one I have on the board here, is I've purely been talking about perturbative quantum gravity, where the background is flat Minkowski space. So you could consider curved backgrounds, or even more ambitiously, non-perturbative classical solutions. Can we really double copy full non-perturbative solutions of Yang-Mills theory into gravity? And indeed, there is an industry doing exactly these kinds of things. That story goes through for very special classes of solutions to the Maxwell equations or the Yang-Mills equations and solutions to Einstein's equations. Okay, on that note, I'll end and thank you for listening and open the floor to questions.
Great, thank you. Thank you so much for a very deep lecture. Very interesting. The talk is open for questions. I have a few naive questions, but I guess we can have this as we go along. Go ahead, please, with the questions. So when you say Yang-Mills, is it necessarily, the Lie group is necessarily SU3?
No, the Lie group can be any. So in fact, all of this just ticks because of the Jacobi identity.
Mm-hmm.
So it's really only the Jacobi identity that we're relying on. So this would go through for any Lie group.
Okay, and I'll always get the Einstein-Hilbert action, is it?
For pure Yang-Mills, you always get Einstein-Hilbert plus axion dilaton.
Yeah.
but you can pick, your input data. You can change what the theories you're putting into the double copy are to get different gravitational theories out. So the most straightforward change you could make would be to swap up pure Yang-Mills for, say, n=4 supersymmetric Yang-Mills. If you double copy that, you get n=8 supergravity. On the other hand, you can even generalize this. I didn't mention this. The two factors of Yang-Mills don't have to be the same. They just have to have color kinematics duality. So I could take Yang-Mills theory and I could tensor it. For instance, it's known that the nonlinear sigma model, the principal chiral model, obeys color kinematics duality. And I can form the double copy of Yang-Mills with the nonlinear sigma model. And so there are many combinations, and what you get out depends on what you put in. So do I have an example of this? Well, no, I don't think I have a non-gravitational example to include here. Yeah, I only have things that give you gravity. But you don't. The gravity isn't the only thing you can get. For instance, you can get Bornfeld-Dirac theories as another example.
Okay.
So there are various things that you can generate by changing your input.
Okay.
You always need color kinematics duality to run in the input. That's
okay. I get your picture. This Chern-Simons is in how many space-time dimensions? The one you discussed.
Yeah, so I was discussing Chern-Simons in the first instance. This is just standard Chern-Simons in 3 dimensions. So you see, I go up to 3 forms. So this is just straightforward Chern-Simons in 3 dimensions. Honest to goodness Chern-Simons theory.
Okay.
Here, when I want to encode self-dual Yang-Mills, you could think of this as either being a 6-dimensional theory, i.e. I've got R4 cross CP1, or you could really think of this as, in a sense, as being in 3 complex dimensions. So you could think of this as holomorphic Chern-Simons theory. So you're in 3 complex dimensions, but it's holomorphic.
Yeah, you said 6. It caught my attention. Would it have to have a signature 3-3 or 5-1?
Sorry, I didn't catch that.
What would be the signature of this 6-dimensional?
So the signature here, you can have. I mean, you can play with the signature of the R4. So typically, one would complexify first, and then you can impose different signatures by taking different real slices. But you could do Euclidean, or you could do Lorentzian if you wanted, or you could do the split 2,2 signature as well.
They would all work, is it?
Yes, they would all work. They all have a slightly different structure, but they would all work. That's
Very
right.
interesting. Very interesting. Yeah. So the Bernd has a question. Is there any link between Lie groups used in Yang-Mills theory and the group of diffeomorphisms of general relativity?
So on the one hand, I'd say that the most straightforward answer to this is no. But in a certain sense, color kinematics duality is telling you that this is in a certain sense, this is the case. Here, in this slide, I have Yang-Mills on the left, say, for instance, and I've got the structure constants of its Lie algebra, and I have the structure constants of the kind of kinematic data. So these are differential operators. And when I double copy, I replace this conventional Lie algebra structure constants with a second copy of these. And what one can show in this process is that from the tensor product of the 2 Yang-Mills theories, the diffeomorphisms appear from these 2 factors. So essentially you get diffeomorphisms of gravity through the tensor product of the 2 Yang-Mills theories. there's two ways of thinking about this. One is where you just, it's this kind of slightly more trivial way where you throw away the Lie algebra structure constants and replace them with a second copy of the kinematic structure constants. Then you get a diffeomorphism invariant theory. Another way of thinking about it is what we introduced as the, I haven't told you about this today, is the convolutional double copy. This is what I originally did with Mike Duff and his PhD students, where you can take two Yang-Mills gauge fields and you can convolve them to generate a graviton, and then the symmetries, the BRT transformation of the Yang-Mills gauge fields, generate the symmetries of the diffeomorphism symmetries, or at least the residual diffeomorphism symmetries left over once you fix the flat background. So that's really like a way where you take two Yang-Mills and you get out diffeomorphisms. Another way of saying this is, so this would be in the gauge fixed picture where you've BRST gauge fixed, you generate the gravitational BRST operator from the tensor product of the Yang-Mills BRST operators. And what that's essentially saying to you is that the tensor product of these Yang-Mills BRST operators, the fact that they give you, what you need is that what color kinematics duality is doing for you is that if you take the tensor product of these BRST operators, that will give you a new BRST operator that's well defined if color kinematics duality holds. That's where color kinematics duality becomes important in this sense. It's ensuring that what you get out are diffeomorphisms. Otherwise, this would fail. Okay.
Thank you very much. So now I'm switched on my video and my mic. So thank you very much for answering my question. May I add an additional question?
Yeah, please, sure.
This is very basic, so I like to picture things. So maybe this is too basic, but if I use your model, so your Yang-Mills gravity duality, if I look closer at gravity, is it then built up from gauge fields? So if I take two gauge fields, do I get a gravitational field, or do I get a graviton from two gluons or from many gluons?
So there are two ways of looking at this, and in one of them, the answer is yes, but it's a little less developed. So in this, I mentioned this convolutional tensor product, and there one would rarely take two Yang-Mills gauge fields, so a pair of Yang-Mills gauge fields, and then convolve them along with what's called the spectator scalar field. So the third field in this game, which morally speaking is like the 0th copy of Yang-Mills, because you can imagine here in this picture, I've taken the red and replaced it with blue, and I get out gravity. But I could have also taken the blue and replaced it with more red, and then I'd have got something that has no kinematic structure constants. It's just got color structure constants. And what I get is a biajoint scalar theory. And that's this scalar that I'm talking about. This biajoint scalar theory kind of mediates between things. And it actually appears there are various ways of discussing this color kinematics duality and double copy. And this biajoint scalar theory is a kind of a common theme. So I can take this convolution where I very literally take a left Yang-Mills field, a right Yang-Mills field. I don't know how I've done that. I made balloons appear.
It looks great. We are talking about color anyway. So.
Yeah. Somehow I made balloons appear. And then a biajoint scalar field that meets in the middle, and it essentially eats up the color structure of the two Yang-Mills gauge theories. And what you come out with, at least to linearized level, is the graviton. So you get something that transforms as a graviton, carries the symmetries of the graviton. Now, you could take this further if you have, this is in this context of this classical double copy I mentioned right at the end. So for special types of solutions, you could do some kind of non-perturbative version of this. And in all of these cases, I'm taking Yang-Mills field, scalar field, putting them together. In the classical double copy, it's literal multiplication as opposed to convolution. And what comes out is a solution to Einstein's equations. This, in a sense, this actually goes back to work of Penrose and I think Rogers. They have this observation that for D-type spacetimes, you can write D-type spacetimes in terms of a South-Dual curvature tensor that factorizes into two pieces that correspond to South-Dual Maxwell fields, plus an extra scalar factor. So you kind of see it's like Maxwell scalar theory. And the scalar theory and all of these pieces, so the two Maxwell South-Dual field strength pieces, they solve Maxwell's equations. The scalar piece solves the scalar field equation. And when you times them all together, you get a South-Dual Weyl tensor that solves the Einstein equations. So in these two contexts, it's very literally you take two pairs of things and you put them together in some way. Now, in the way I've been describing it, it's more like a replacement rule.
Okay.
So up here, it's more like, you see, it's more like about how do you, it's not so much that you take two copies of Yang-Mills and you put them together. It's really, given the data of Yang-Mills, how do I get the data of gravity? And there's this replacement rule where you say, well, rather than valuing the fields in the kinematic vector space encoded by I here and the color vector space encoded by A here, I strip away the color and I replace it with another copy of the kinematics. And in a sense, this is I mentioned at the beginning that the L-infinity algebra corresponding to Yang-Mills theory can be factorized into, let me go, yeah, I don't need to go that far back. I can go here. It can be factorized into the color part and the C-infinity algebra part. And then we learn when color kinematics duality is true, that the C-infinity algebra isn't just a C-infinity algebra. It's more. It's a BV box infinity algebra. And then if I strictify, I get a BV box algebra. So I have some BV box algebra, this B thing. And then you can see here, this is my L-infinity algebra of Yang-Mills. And you could ask the question, well, how do I get the L-infinity algebra of gravity? If I didn't know what it was for gravity, if I hadn't discovered the Einstein-Hilbert action, what could I write down? Well, you kind of want to take this guy and tensor it with itself again. That's kind of like the double copy. It's like taking two copies of the kinematic part of Yang-Mills and tensoring it. And that's what we're doing here. The problem is, if you take the tensor product of two graded commutative algebras, you get out a graded commutative algebra. You don't get out an L-infinity algebra. This is just, you know, the generalization of, say, if you take the tensor product of two Lie algebras, you don't get a Lie algebra. But if you take the tensor product of a commutative algebra with a Lie algebra, you get back a Lie algebra. So if I take two commutative algebras and I tensor them, so these are commutative algebras, B left and B right, I get another commutative algebra, not an L-infinity algebra. Essentially, this is how the product would be defined.
So the L-infinity algebra is not closed on the tensor products then.
So you can take tensor products of L-infinity algebras, but so the general rule that comes from this operatic structure is that if you take commutative with commutative, you get commutative. Commutative with Lie, you get Lie. Lie with Lie is not defined generically.
It's not defined. Okay, so
it's
not defined. So you cannot even define a tensor product of both.
There's no canonical definition of what the Lie.
Okay, so you can simply not form it.
Yeah. There's no canonical definition. So you can see for a commutative algebra, there's this very, very canonical definition of what you do, right? If the product on the tensor product here is just the tensor product of the products. Now, if you replace this M here with rather than being graded commutative, you replace it with a Lie bracket, and you try to enforce the Jacobi identities, you realize this won't hold, and then and there's just no canonical construction to take Lie tensor Lie.
Okay.
But there is a canonical construction to take Lie tensor commutative, and that's what I have down here. So you can take a Lie bracket and a commutative bracket, and you get out a Lie bracket. So now that does work. So this gives us a notion of how to construct these tensor products. So now it really is, rather than taking pairs of fields, well, I suppose in a sense I'm still taking pairs of fields, because the arguments that would go into these brackets would really be the color stripped Yang-Mills field left, tensor the color stripped Yang-Mills field right. But it really is just a straightforward tensor product in this case. So
Okay.
yes, the picture generally is one should think of gravity as being the gravitons as being the tensor product of gauge fields.
Okay.
That's the picture to have in mind.
Okay.
The details are a little more involved, but that's the picture.
Involved.
Yeah.
Thank you very much.
On that point, does that mean also that the spin to graviton is not fundamental, as if it's a composite of two spin one gauge bosons?
Yeah, so that's a really good question. This is not a, I mean, in a sense, this is not a composite in the traditional sense that you know the action is not going to decompose into just you know the left and right pieces.
Mhm.
It doesn't separate out in that way.
Mhm.
So I'm not sure I'd characterize it as being a composite in the traditional sense. I mean, you know, the worry you'd have would be the Weinberg-Witten theorems that kind of prevent. They tell you that straightforward composite understanding of the graviton is just not possible.
Yes, that is true. Yes. So suppose so someone is looking in the lab for a spin to graviton. Would they have a takeaway from your picture, or they can go ahead with what they are looking for, a spin to boson?
Yeah, no, you'd be looking for a spin 2 boson. I don't think that would change. What changes is what you need to calculate predictions for it. I mean, or
Yes.
you know, you can just put in the data of a Yang-Mills gauge theory instead of putting in the data of graviton. So, I mean, I don't know. Is there a philosophical point of view here that actually says gravity really is the product of these two gauge theories? I mean, I suppose in a sense, given that perturbatively, for scattering amplitudes on flat backgrounds, you can compute one given the other, at least semi-classically. You might argue that, well, then one really is just the double copy of the other, and there is no new data in gravity over Yang-Mills. Of course, this completely ignores non-perturbative questions. It completely ignores renormalization. The fact that gravity is non-renormalizable isn't addressed by this. So, you know, even if you took that philosophical stance, which I think you could, it wouldn't get you to all of gravity. That, you know, this is just at the moment a constrained part of it. One could also take the other point of view and say, well, this is just now a tool. It's just that gravity really is gravity as we know and love. And this is just some other way of articulating or understanding it. And that, I mean, you could take a pragmatic attitude, and that's what has directed a lot of this field in recent years. They've taken the pragmatic attitude of, well, we want to compute stuff in gravity. We've got very good at computing stuff for scattering amplitudes in QFT. Can we leverage some of that machinery towards computing non-trivial things in gravity? And indeed, you know, Saemann and colleagues have done reasonably remarkable calculations along these lines. I mean, the stuff, it certainly to me seems very impressive what they've managed to achieve. At some stages, they've outcompeted the best other technologies for these calculations. I think maybe, well, yeah, I'm not up to date on that, so I don't want to make any definitive claims. I don't know where those calculations lie at the moment, but at some stage they were outcompeting the cutting edge.
But when we say GR is not renormalizable perturbatively, but Yang-Mills theories are, where then, I mean, why is this happening then? If GR is the square of Yang-Mills, where did I lose the renormalizability?
Yes, so that actually enters, I mean, what I suppose probably the most straightforward way of convincing you that Yang-Mills isn't, the renormalizability of Yang-Mills is insufficient is if actually you look at what happens in the original double copy in this kind of a picture here, the power counting changes, right? These ends are built out of momenta. So in doubling the ends, you change the power counting. So there's no a priori good reason to suspect that gravity would land up being renormalizable because Yang-Mills gauge theory is. Now there are, I mean, part of the motivation in the early years of this program was to understand UV divergences in perturbative quantum gravity. And some interesting puzzles come up. For instance, there are examples where one would naively expect a divergence in supergravity to appear, but it does not appear. And these are like, you know, the n equals 5 supergravity at 4 loops, and this is kind of surprising. And the way they showed this was actually using the double copy to compute these amplitudes through the double copy. So color kinematics duality was happening. And for a period, at least, I don't know what the status is now, there were speculations on maybe color kinematics duality is actually improving the UV properties of gravity. On the other hand, the fact that this divergence didn't appear in n equals 5 supergravity kind of suggests that maybe there's not something fundamental going on, because I don't think anyone thinks that n equals 5 supergravity could be UV finite, perturbative UV finite. If this was happening, especially for, say, n equals 8, the maximally supersymmetric theory, you might imagine that something special was happening there. So depending on which way you look at it, you could either say this is nice evidence for maybe there's some way to ameliorate the divergences in perturbative quantum gravity through color kinematics duality, or you could turn it around and say, well, because this is working in places we wouldn't expect it to work, we expect it to just fail at higher loops. And the jury is just out on this question, I think, at the moment. We just don't know the answer.
Yeah, I'll come back. Thanks. That's very interesting. I'll come back for more. But I think Anthony has a question. Kindly go ahead, please.
Hi. Thanks very much for your talk. Very interesting. I just wanted to ask again, I was going to ask a similar question to Jinder about the relationship to quantization of gravity. So at some points you were talking about how taking 2 copies of Yang-Mills and convolving them, you were taking a quantum approach, but if you multiply them, it was classical. And so you have an idea of where you're going to in terms of the output, whether it's quantum or classical, but I didn't fully understand how that affects what you're looking at. So in particular, it looked as though you just got classical gravity coming out, you know, with an axion and a dilaton. What level, if you carry out what you're doing at a quantum fashion with a convolution, is it different from what you've shown already?
So probably let's put aside the convolution for the moment, because that perhaps confuses things, and just stick to this amplitudes double copy. But yes, you're right that the final thing I talked about for these non-perturbative solutions, that was a purely classical statement. So this is about classical solutions to Yang-Mills and gravity. So no quantum effects there at all. When I talk about in the quantum case, I'm really talking about perturbative quantum gravity around a flat background. So I'm just expanding the Einstein-Hilbert action around a flat background and applying the usual perturbative Feynman diagrammatic rules to construct amplitudes and computing amplitudes to whatever loop order I'm interested in.
All right.
So the statement is that if you have color kinematics duality in Yang-Mills to all loop orders, then you can double copy to get graviton amplitudes to all loop orders. Now, importantly, this is prior to regularization, right? This is the level of the integrands themselves prior to integrating. So I take this integrand from Yang-Mills and I generate from it this integrand of gravity, and this is to any loop order. you still have to do the integrals at the end, and then regularize and renormalize, and then you yeah. So when I talked about perturbative quantum gravity, I really meant to all loop orders. That's what I meant. So maybe I should also clarify that we don't know that color kinematics duality holds to all loop orders for Yang-Mills. The two things we do know is that color kinematics duality for Yang-Mills holds, or super Yang-Mills holds to low loop orders, where people can do explicit calculations and find color kinematic dual representations of the amplitudes. So if you just take the Feynman rules of super Yang-Mills and compute the amplitudes, these kinematic numerators will not satisfy color kinematics duality. You have to do some massaging. And indeed, we already saw a baby example of this for loops. If I take the Feynman rules as they're given here, these numerators, without the tildes, NS, NT, and NU, they won't sum to 0, despite the fact that CS, CT, and CU sum to 0. What I had to do was absorb this 4-point function into them. Then they do, only then. So there has to be some massaging of the Feynman diagrammatic picture to get color kinematics duality to work. Now, you can do that at loop level in these low order cases. And so we have examples where it works at loop level. Then you can ask, can I get it? Can I prove that it always works to loop level? Now, what we can prove, and what this part of our work is about, is that we can show that there is a rewriting of the Yang-Mills action into this form, where these, so this is now just some action with some infinite tower of fields, where you see that these differential operators satisfy the Jacobi identity as operator equations. And that means that you can imagine constructing your Feynman diagrams directly from this action, right? The vertices will have these blue capital Fs and red lowercase f's at each vertex. So that, and because the both F's satisfy exactly the same identities, whenever you have a triple of diagrams where the red F's, the sum, where the structure constants, where the color factors built out of the Lie algebra structure constants satisfy a Jacobi identity, the corresponding kinematic factors will obey exactly the same Jacobi identity, because the pairs of F's are algebraically indistinct from each other. They just see no difference. So you can show that the integrands, the loop level integrands you get from this action manifestly satisfy color kinematics duality. And because this is for the Batlin-Vilkovsky or the BRST action, it's got all the ghosts and everything you need for your loop level amplitudes are included in this action. In principle, the next thing you want to say is, oh, we've proven color kinematics duality at the loop level. But we committed a sin in putting it into this form. We actually don't know if we need to do this, but it might be that we need to make field redefinitions of this type that include non-local terms, such that when you compute the Jacobian of this field redefinition in the path integral, you pick up a counter term. Now, what is that counter term doing? Well, it's restoring unitarity. So what we've given up by writing it in this color kinematics dual form, we've given up manifest unitarity in favor for manifest color kinematics duality. And it might be at some loop order that to restore unitarity, you need a counter term that will break the color kinematics duality symmetry. So the question, if you say that you're happy where you just want loop level integrands prior to regularization and renormalization to satisfy color kinematics duality, our job is done. But if you want that to continue to hold once you introduce counter terms corresponding to regularization, renormalization, then the color kinematics duality still may fail. So at the quantum level, the jury is still out for this theory. In fact, there are there are very few examples where we know exactly what's going on. So Chern-Simons, because everything works perfectly for Chern-Simons off shell, we have this perfect color kinematics duality. There, in principle, it holds to all loops. So the quantum theory to all loop orders is color kinematics dual, except there are no scattering amplitudes for Chern-Simons theory, so there's nothing to check.
Yeah.
Another place where we can do it is for self-dual super Yang-Mills theory through this holomorphic Chern-Simons. But again, in the maximally supersymmetric case, there are no amplitudes to check. And in the non-supersymmetric case, there are one loop amplitudes. Okay, that's good. But the problem is that the twistor theory itself has a twistorial anomaly. So there's another anomaly spoiling things. It does kind of seem like there's a bit of conspiracy. Whenever you solve one problem, another problem arises. So conservatively, although there's lots of evidence for loop level color kinematics duality, it may just not hold for Yang-Mills theory. That's possible still. Not to say that there aren't examples to low loop orders. So you can find color kinematics duality up to 4 loops, for example. Yeah.
Okay, thank you. So I have another question. So traditionally, there has been a lot of attempt where people talk of trying to cast gravity as a gauge theory. In particular, the loop quantum gravity approach, where Ashtekar begins to get his new variables as self-dual SU2 Yang-Mills. Over there, no squaring is involved. Is that correct? Am I wrong there?
Yeah, that's correct. So before it used to be. I mean, it's a very natural question, and indeed, it used to be that I would begin my color kinematics duality talks talking a little bit about the other gauge theory approaches to gravity to draw out this distinction. So, I mean, it has a long history going back to at least, well, I don't want to make definitive claims about who was the first person to think about gravity as a gauge theory, but Utiyama and Tom Kibble had early papers where they considered gauging the Poincare group.
Right. Shyam
yeah, which is like a very direct, you just give you have as your color group, the Poincare group, and you gauge it, and you actually get very far. I mean, you can take that story quite far, and it's very close to really being gravity. And then, as you mentioned, there's the I mean, the Ashtekar variables have the same kind of feel, and there are certainly, formulations that are literally Einstein gravity, but where they have a local, thinking about it in the tetrad type formalisms where you have the local Lorentz indices, that's very close in spirit as well. So you're right, there is no real, I mean, in those cases, I didn't need to talk about double copying. At one stage, we were considering how you could get these tetrad type formalisms by taking two Yang-Mills theories, where you think of one as carrying world indices and a color index, and the other carrying local Lorentz indices and a color index.
Right.
And then taking this biojoint scalar field to glue up the color indices and then get a tetrad out. So you might think you could get to these other places, but I don't think that they're not contingent on each other. None of them depend on one of the other working.
So you were saying that what you are doing is, in a sense, quite different from what they are doing, is it?
I feel like there are places where you could connect this. It would be possible to take the ideas of the double copy and put them into more established approaches to writing gravity in terms of some kind of gauge theoretic data.
So like they will start from a Yang-Mills connection, then you need a soldering form to go to the spin connection on the base manifold. That's not involving any squaring, is it?
No. So although I think you could connect these pictures up in some way, I don't think one is contingent on the other. So I don't think you need the double copy for if you want to go ahead and do loop quantum gravity, you don't have to use the double copy in any way.
I see. Okay. Okay.
That doesn't mean that there isn't some way of bridging the gap, but
Okay.
I think they're independent. They're sufficiently independent that you can run them both at the same time and not have to tie them up.
Okay. But fundamentally, if I try to make a claim that only one of them can be correct, would that be an unfair kind of statement to make?
It would be premature.
Ah, very good. Excellent. Thank you. Thank you. Yes. Yes.
Hello, Professor Leron. I have a question that when we say n equals to 5, are we entering into the framework of string theory, or can n equal to 5 Yang-Mills theory exist as an independent theory from string theory?
Yeah, okay. There's two things I want to say about that question. It's a good question. The first thing is, yes, you could. No one stopped you from regarding n equals 4 super Yang-Mills as an independent theory. Now, the motivations to do so, while they could be questioned, and one way you could motivate it was to say, well, this is part of the tapestry of string theory, and if you want to run the string theory program, then you have n equals 4 super Yang-Mills sitting in there. Be one way of motivating it. Another way of motivating it would be that it's just like it's a kind of more tractable version of Yang-Mills theory. It's something that you can do calculations in. It's the simple harmonic oscillator of the 21st century, some people have said. It's a good place to do examples. The other way I'd like to answer your question is to say that actually this double copy has a string theoretic provenance. That's not to say it's contingent on string theory. I didn't need in my talk to mention string theory at all. Pure Yang-Mills, if it has color kinematics duality, implies the double copy. Full stop. No string theory needed for that statement. On the other hand, you can trace the origins of this in a certain sense back to string theory through the KLT relations. So I am just running as quick as I can back to my first slide. You can see I've made too many slides. Here. So I listed some of these early works, and I mentioned Feynman, but of course, this rarely only, I would say it's fair to say, only got teeth with the Kawhi-Llewellyn tie relations, which say that closed string amplitudes can be written as sums of products of open string amplitudes. Open string amplitudes in their low energy effective field theory limit include Yang-Mills gauge theories in general, and closed strings in their low energy effective field theory characterize gravity or supergravity. And the picture is a very literal picture, right? You're taking two open strings like this, you glue them together to get a closed string. This has gravitons, these have gluons. So and effectively, in a certain sense, you can think of these double copy relations as taking the low energy effective field theory limit of the KLT relations of string theory. Now, interestingly, the KLT relations of string theory are only known at tree level. Okay, let me rephrase that. To the best of my knowledge, which is certainly out of date, so there may be progress on this front, but the last time I was aware of this, or looked into this, they're only available at tree level, and their loop level analogs were not spelt out. For Yang-Mills, we have loop level examples of the double copy, and crucially, we've learned that color kinematics duality is one of the key things that gets it running. And one of the open questions is, can you take color kinematics duality and realize it for the open strings, and therefore try to expand the KLT relations that relate closed strings to stitching together two open strings and make that more concrete, or generalize it beyond the tree level, I should say. So yes, so the answer is there's a clear relationship to string theory, but it's not contingent on string theory.
Okay.
I like to ask a question on another thing, which is when we try to quantize gravity, we often face the question of singularity, or in either so there is also some kind of singularity in QED also, which we call divergence, which we remove by using renormalizations. So my question is that. What makes this non-renewable renormalizability of gravity? What makes it renormalizable?
That it just won't be renormalizable. I mean, so you will get what the double copy generates. So let's say of pure Yang-Mills, leave aside supersymmetry. It will generate Einstein-Hilbert gravity coupled to an axion dilaton. And barring some miracles that I have no reason or nobody has any reason to believe will happen, that theory will be divergent. In fact, we know Einstein-Hilbert gravity coupled to matter diverges for explicit calculations. And that's Sagnotti and Groth. And so that will be divergent. And what we're getting from the double copy are precisely the amplitude integrands of gravity. So if we know they diverge in gravity, and we know it's non-renormalizable, what we're getting out of the double copy will be non-renormalizable.
Yeah.
Where it might be interesting is where you don't know whether the theory is perturbatively renormalizable or not. Now, I think the general consensus in the community is that all supergravity will diverge. I think that's the most conservative attitude. Will be non-renormalizable, I should say. Some are more cautious in this statement and say, well, actually, we don't know. Maybe n equals 8 for some because it has a significant number of symmetries beyond the usual ones. It's got a large U-duality symmetry. It's got a large amount of supersymmetry. Perhaps it could be perturbatively finite, possibly.
Mm-hmm.
There, we don't know the answer. No one's done a calculation and observed a UV divergence in that theory. That no UV divergences have actually been computed in that theory.
Okay.
We don't know whether the symmetries of the theory are sufficient to prevent those divergences or not. There's no solid statement about that. There was recent work, very recent work by Renata Kalosh that I haven't looked at yet. But glancing at the abstract, and I hesitate to say this because I don't know if I'm recalling this correctly, but glancing at the abstract, I think the suggestion was that the symmetries of n equals 8 will not be sufficient for UV finiteness. But the conservative statement is that the jury's out, we don't know. And maybe there's some space for some interesting things to happen with the double copy there.
Okay. Thank you. I want to take you to sort of ask your feedback on a related renormalizability question. Let's have a look at, let's say, the weak interaction. We know that by itself, it is not renormalizable, but the unbroken electroweak symmetry SU2L cross U1Y is renormalizable. So some work that we are doing, revisiting E8 cross E8 unification, which was once very popular in string theory, but then they gave up. So we have a different way of looking at E8 cross E8, which in its branching, in one part, one of the E8 gives a SU2L cross U1Y. The other E8 is giving a SU2R cross a U1Y prime, let's say. And we are trying to justify that this SU2, after symmetry breaking, will give rise to general relativity. And my U1, we have some ideas with probably Milgrom's Mond, so that a fundamental pre-gravitation theory is not GR. It is a SU2R cross a U1 theory, which we would expect to be perturbatively renormalizable for the same reasons that the electroweak theory is renormalized. So with the moment I generalize GR from a SU2 Yang-Mills theory to a SU2 cross U1 Yang-Mills, I see life improving. Would you say, no, this won't work kind of thing? I'd be very interested in what you think of this.
Do you have some published work or some preprints that I could maybe look at?
We have the E8 cross E8 theory, standard model, branching and all. But quantization of this SU2 cross U1 is something we are still looking at. The idea is the following. One of my collaborators, Samuel, if he's here, I would like him to, he knows it more than me. So what we are saying is that the electroweak theory per se, suppose I have two copies of 4D space-time. I will take the electroweak theory and write it as a theory of gravitation on the second 4D space-time. At the same time, I'll take general relativity cross this U1 in our space-time and write it as a SU2R cross U1 gauge theory. I want to treat the weak interaction, electroweak and this gravity cross U1 precisely on the same footing on two copies of 4D space-time. This is something we are doing. So see, we are sort of excited that SU2R cross U1 would be a renormalizable gravity theory. Would you have a first reaction to that? I would be interested. Do you see any reason that I can't make such a claim?
So no, I mean, as a first reaction,
Am I
no.
telling
But
you too little? I'm probably telling you too little right now.
yes, I think I'd want to have a look at some of the details. But I'm really curious because it sounds like you've got a pair of space times.
Right. So what is happening when in our E8 cross E8 branching, the string guys started with saying there's anomaly cancellation in 10D space times. Then now let's compactify 6 dimensions to get our space time, and that gets into a problem. What we are finding is that this E8 cross E8 is giving me two copies of SU3s as internal symmetries. One is QCD color, and the second one is a new SU3. We call it SU3 graph. It's a new force which we have to live with. And the space-time actually is 6-dimensional with a signature 3-3, SO33, which can be written as having embedded in it two copies of 4D space-time, actually with relatively flipped signature. The other one will have 3 time-like and 1 space-like direction. And we are trying to say that the electroweak theory is the gravity of that space-time, and GR is the gravity of our space-time. And on the whole, these 6-dimensional space-time have 2 extra time-like dimensions. So our universe has 3 time-like directions and 3 space-like, of which our apparent 4D universe is a subset.
I see. So, but the gravity that you understand as living in one, I suppose, in our half, how is that different to how is it distinguished from Einstein-Hilbert gravity?
The difference is the U1. What I call gravity is actually gravity plus Mond, where at low accelerations, Milgrom's Mond becomes significant. At high accelerations, general relativity, the Einstein-Hilbert. So the action that I would write would Einstein-Hilbert action plus a U1 gauge theory, whose actually quantum of charge is square root of mass. I want to have another question for you later. So just as the quantum of charge is the electric charge for a U1 electromagnetism, the quantum of charge on my space-time for the U1 is square root of mass. And of course, the source for GR is the energy momentum tensor. So here we see something like a squaring. The GR is some sort of a squaring of the U1, because in GR, the source charges are proportional to mass, not to square root of mass. But in this U1, the source charge is, we have a current which is proportional to square root of mass, root MC UI, which when I square would give me the conventional energy momentum tensor MC UI UJ kind of thing.
I see. I think I mean it sounds interesting. It's sufficiently outside of my comfort zone that I'd hesitate to offer an opinion. I think but I'd be curious to have a look at the papers, and it sounds interesting. I'd like to understand if there are some connections to the double copy.
Yeah, great. I'll send them over to you. And probably my last question, it was about the source term. So if you have color kinematics duality, that lets you write graviton amplitudes as square of the Young-Mills amplitudes, does that mean there is some sense in which the energy momentum tensor on the right-hand side of Einstein equations is also the squaring of some first-order gauge current?
Yes.
But there, Mike, the question would be that I know that the energy momentum tensor is proportional to mass, not to square of mass. And then does that mean the gauge current is proportional to square root of mass?
So there is work on this, and from a number of points of view, it's largely in the context of the classical double copy. My colleague Silvia Nagy has done work on this, where they really consider sources and fields, and there they really double copy the sources as well. And typically the charge that I don't recall how the relationship between the charges go, but on the one side you'll have some, if you're just doing Maxwell, you'll have some electromagnetic charge, and that will land up being related to the gravitational charge in the double copy. So you'll need to make some identification between the Yang-Mills or Maxwell charges and the gravitational charges, which I think is largely just done on dimensional ground. So this is something that, you look what you put in, and you say, well, this has to be the identity between these two things. So I'm not sure one could say you've derived it as such, but, given that you're double copying the sources, you're led inevitably to identifying the gravitational charge in terms of the Yang-Mills charges. Or
that would be something profound, no? That would be something profound and fundamental.
So I skipped to the end. The list of references that I give at the end is probably the most helpful in this context.
Okay.
So that works. I mean, perhaps you could start with this paper by Ricardo Montero, Donald O'Connell, and Chris White. And the paper I was talking about, where they very much explicitly double copying the sources, is in this paper. But in this classical double copy story, you really want to, for instance, they can double copy, they can generate the Schwarzschild solution from some solution from Maxwell, and there the Maxwell solution is sourced by an electric charge.
Right.
There's a Coulomb charge, and the gravitational is sourced by a point mass charge, the Schwarzschild solution. So you do get a relationship between the charges in that sense.
That's very interesting. And it would be something like the square of the electric charge is proportional to the mass.
Right. Let me think. It must just follow from dimensional grounds, but it's not. I suppose you're right. Yeah, I'm not sure.
That looks, because in my work also there is there's a balance between electric charge and square root of mass, not electric charge and mass, but electric charge and square root of mass. are to be treated in some sense on the same footing. And the
Right.
square root of mass comes with two signs, plus minus square root of m. Both will, on squaring, will give a positive mass. Mass is positive, but when I take the square root, I have a plus sign and a minus sign outside. So I get two signs for square root of mass, just like two signs for electric charge. So at that level, there is in that sense, there emerges a connection with gauge theory, which is a little bit perhaps like what
Yeah,
you
no, that sounds very familiar. I mean, I don't want to guess at what they actually concluded, but that sounds very familiar.
Okay, I'll definitely see these papers. Great. That would be Montero, Cornell, and White, and the second paper also.
That's right, yeah.
Yeah, Nampuri was at our institute long ago.
Oh, is that right?
Yes, right. So there's a question in the chat from Samuel Wesley. Is it possible to formulate a background independent gravity theory using this double copy approach?
Well, I mean, I suppose the first answer to that is the story that I've been telling is very background dependent. I'm really doing things on a Minkowski background, perturbatively. So my story is very far away from being background independent. To a degree, all of the generalizations to curved backgrounds or non-perturbative solutions, I mean, so for instance, there are some generalizations of this to non-flat, both Yang-Mills and gravity backgrounds. So you could take plane wave solutions to the Yang-Mills, and you do perturbation theory around that. But it's all very background dependent. So at the moment, I would say the answer to that is no. I mean, not to say that there's no way of doing it, but there's no obvious route to it.
Okay, thank you. Thank you.
I have also a question. Can I ask?
Yeah, please.
Professor Leron, when we talk about the Yang-Mills as the score of gravity, there is also some kind of prior theory, like in a gauge sense, which is quantum loop gravity. In quantum loop gravity, there is a thing called the Hamiltonian constraint, which is essential to it. So my question is that in this kind of a specific theory, like Yang-Mills as a square of gravity, is there a kind of constraint in this?
Well, I mean, in the sense that Hamiltonian constraint is a part of the data of Einstein-Hilbert gravity, yes, it's there. In the sense that what we're really doing here is perturbatively, we're doing perturbative quantum field theory on a flat space-time background where we're scattering gravitons. We're very much turning the QFT 101 handle of you have some action on Minkowski space, and in this case for gravity it will involve a spin-2 field. You find it has a kinematic term. You invert the differential defining the kinematic term with the propagator away from the cohomology, the on-shell states, and you use that to write down a propagator in some gauge, because this is a gauge theory. And then you have the Feynman vertices given by the higher point interactions, and then you just compute the scattering amplitudes. So in that sense, the kind of non-perturbative quantization that loop quantum gravity is driving at, and the kind of deep difficult steps they're just not a part of this story, because we're really just doing perturbative quantum field theory of a spin-2 particle on a flat background where the interactions are derived from the perturbative expansion of the Einstein-Hilbert action. But of course, you could then say, well, this comes from the Einstein-Hilbert action, and that has the Hamiltonian constraint, And then you could say, well, I now want to quantize it non-perturbatively or go to the Hamiltonian formalism. And then indeed that would be there. But it's not calculationally, it's not a part of this story in any deep sense.
Thank you. Thank you.
I have also a question.
Before you think we should close, you can write to Leron, please, because it's 2 hours now and you're probably exhausting him. He's been talking for 2 hours.
Well, he certainly has given us magnificent value. But Leron, how do you feel? Do you just want to take one or two more questions, or?
I could take another question. I mean, it's
Okay, we always
it's 6
hate
o'clock on a Friday, and I still have my commute home.
Okay, last question, Jitu.
Okay, thank you for allowing me to ask a question finally. When we talk about the Hamiltonian constant of loop quantum gravity and also Yang-Mills, Yang-Mills clearly has a connection to string theory, string theory. Then can we somehow use the Hamiltonian constraint to introduce a loop quantum gravity in a string in the framework of string theory?
I mean, just be honest, I have no idea. I mean, I suppose on the one hand,
actually, my
loop
question
quantum
is
gravity
can we at least think of doing such thing like in the during the second string revolution, no one actually thought of unifying the whole string theories like type 1, type 2, heteroid SO2 and E8 cross E8 like we can unify these whole string theories in the M theory as a limiting. So can we think actually at least even think of introducing this in a string theory framework?
I mean, loop quantum gravity?
Yes. Like also there are also loops in our string theory like Polyakov loops and Wilson loops, etc.
Could I make a remark, Leron?
Sure, please go ahead.
So just to answer you, Jitu, we are also developing a E8 cross E8 theory of unification. Interestingly, the starting symmetry group is the same as in heterotic string theory. And for probably similar reasons, our reasons come from working with octonions. Theirs come from anomaly cancellation in 10D. But 10D is special because of the octonion. The special linear group SL20 is the double cover of SO19. And clearly the octonions are playing some role why string theory works in 10D. And the branching that we do of E8 cross E8 tells us that we don't get general relativity right away. We get an analog of the electroweak theory, the right-handed analog of electroweak theory, SU2R cross U1. This SU2R is very much like Ashtaker's gauge picture of general relativity. So in that sense, we think that Ashtaker's LQG is embedded in our E8 cross E8, but the U1 is very important. Just as the U1 is important for electroweak, we cannot quantize the weak force, but we can quantize electroweak. So same way, we cannot quantize general relativity, but we can quantize general relativity tensor product with a U1. That is and this U1 has a physical interpretation. It should be detectable.
Professor Tejinder, you told that we don't get the Einstein-Hilbert action straight away. So can we at least get the Palatini action straight away?
Yes. Samuel, do you want to say something about that, what you are doing?
Hello.
Yeah, please go ahead. I think you
Yeah,
could
am I audible?
Yeah, you could answer Jitu better than me, I think.
Yeah, what was the question again?
Well, what is when we say GR is SU2R cross coming from SU2R cross U1, what is the action you would write? Is it the Palatini action?
Well, Palatini, yeah, that's a formalism.
Mhm.
Yeah, and
Yeah, you could answer, Ritu, by saying what was your action principle from which you get GR in the end? Hello, are you there? I think we probably lost him in the connection. So, Jitu, you can talk to Samuel. I'll put you in touch with him.
Thank you.
Okay, great. Leron, could you kindly stop sharing so that we can see everybody on the screen? Yeah, great. There's not many of us left, I think, but it was a great talk. I really enjoyed, especially also the discussion session. Learned a lot from talking to you. So, do you have any morals for those who try to unify gravity with the standard model?
I don't think I do. Not beyond the standard folk laws.
Mhm.
I don't have anything wise to say at this moment.
Okay,
I wish I
great.
did. If I
No.
did, I would write up a paper and publish it.
Yeah, sure. Well, it's great talking to you. Yeah,
No, thank you for inviting me. It was a pleasure. I really enjoyed it. And the conversation was very nice.
yeah.
And I hope to come along to some of the future editions.
Great. So this is
Please do that. We would be only too honored to have you, and I think you'd be contributing a very great deal.
No, I'd be very happy to. I've had teaching on Friday afternoon. It's the only reason I've not been able to come.
So next week we have a related talk on Gravi-weak unification by Antonino Marciano, and yeah. So I think that's all I want to say. Thanks so much for staying
Yes,
for
thanks very much again, Leron.
long
It's
discussion.
absolutely fascinating.
Okay, it's a
Much
pleasure.
above my pay grade, but still, I got glimpses of the scenery, and it was very exciting.
Thank you.
Yeah.
Thanks. It's very kind.
Thank you very much, also from my side.
Okay.
Thank you.
Thanks a lot. I'll part ways now.
Okay.
Yeah, please go ahead.
Thank you.
Bye-bye.
All the best. Join us again as soon as you can.
Sure. Looking forward to it.
So the next talk is in 1 week, correct?
No, it's in 2 weeks.
In 2 weeks. Ah, okay, in 2 weeks. Okay.
June 7, and after that it's your talk, is it?
That is my talk, yes.
June 14 is yours, and then Siddhant on June 21. We'll have 3 successive
Yes,
talks.
yours is on the 14th, Bernd, isn't it?
The 14th. Okay, thank you. I think, is it on the list?
Yes.
Also,
Yes.
Yes,
It's
it is on the list.
schedule.
Also with the new date, I mean.
Yes.
Yes.
I think
great.
so.
Okay, then
I must recheck, but I'm quite certain it's on the list.
Okay, good. Then
the new date is on the schedule. Yes.
Yes.
By the way, Milgrom has also agreed. It's sometime in December.
He's going to give our very last talk of the year in December.
The last talk.
The Christmas talk, so to speak.
Is there will there be any talk from my Professor Michael Berry?
From Michael Berry? Well, I can't remember. Did Michael accept an invitation?
We didn't send one.
Would we like? I'm going to be seeing him in in the near future, because he's coming to this meeting in Askloster in Sweden in honor of Basil Hiley that I've organised in July.
If it fits into this theme of particle physics, quantum.
Well, that's what I'm thinking. I mean, of course, his ideas are absolutely fascinating, but he's actually giving a sort of very general overview lecture there about the history of notions of geometric phase in physics, 19th century.
His work is, of course, work is absolutely great.
Yeah, I mean, it depends how narrowly you want to keep the focus on. We had said this year that we were going to try to broaden things out beyond extensions of the standard model, even via the octonions. So I put it this way: we should certainly have him in mind, perhaps for 2025. For sure.
Or if you want him later this year, that's also
sure. That would be excellent.
We still have 3 free slots. And
I was going to ask you. We still have three free slots. There were a couple of people I wanted to suggest to you, but perhaps we could do that, as it were, offline.
Yeah,
some point in the next.
We need to have a meeting soon.
And yes, in the meantime, well, again, that was, I think, a great vindication of the initiative we took in setting up this series of talks. It was extremely interesting. There was one question I wanted to ask, but I couldn't quite summon the courage, which was to do with how far this, particularly the question that you were asking towards the end of the discussion period, about mass and the square of mass in relation to the Maxwell theory, and that whether there is any connection with these speculations about the role of square of mass constructions and the suggestion that mass is in fact related to sorry, excuse me, I'm having a senior moment, the conformal rescaling.
Very, very good point. I think the square root of mass theory, the UN theory, perhaps is conformally invariant.
Well, this was the speculation. I couldn't quite sum up the courage to ask Leron, because he's obviously way above my pay grade in terms of his knowledge of the detail. But that was my kind of guiding intuition. There might be some connection here with this intuition that mass is ultimately the expression of conformal rescaling.
I think we have a very good point. The square root of mass, I think, has strong implications. It's like also telling us there's a square root of the Dirac equation, you see, because the Dirac equation is proportional to mass.
Exactly.
Mass,
yes.
Square root of mass is fundamental.
Yes.
I have no choice but to take the square root of the Dirac equation.
Yes. It's funny. That was a point which came up in discussion between me and Basil Hiley just the other day.
Right. Just to complete,
I also have a question similar to this.
When I'll just complete. Yeah. So what it looks like is that the Dirac equation is related to a Clifford algebra, and these are quaternions over real numbers.
Exactly.
What we seem to need is quaternions over Grassmann numbers. You get me?
It's just such an extraordinary coincidence, because this is the very topic that I was discussing with Basil just 2 days ago.
And great. And when you square a quaternion which is over Grassmannians, you get an ordinary quaternion over the reals, because a product of two Grassmann numbers is an even grade Grassmann number, which they commute with each other like real numbers. So it's like we want to write a Dirac equation over Clifford algebra over the field of Grassmann numbers. You talked to Basil about this.
Exactly. I must get back to you on this, because I need to refresh the notes that I made. It was a very intensive discussion, but no, there was the idea was very much on these lines, and indeed there was also a suggestion with this connection, as you say, with but the really interesting point was there. Basil has a way of getting the twister construction out of this as well, but in a way which doesn't bring in Roger's way of doing it through the flag picture and through, as it were, making the complex holomorphic space fundamental to the construction. Really, this can be done really in a way I think up more convincingly at simply staying within the reals, in the way that Dyson, in fact, suggested long ago.
Say that again, yeah.
The way that Dyson suggested long ago, that we could do all of this construction that in Roger's case, when it comes to the twisters, involves the complex holomorphic space, without in fact having to go into the having to use the imaginaries, without having to use the complex numbers at all. It could all be done staying within the reals, but provided that you had a sufficiently general geometric algebra.
I think there's something new which we need to add on. I totally agree. That's why the square root of mass, I think, is so important quantum number, which has not been appreciated so far at all by particle physicists.
Yes. I think that's right. Well, there's a great deal for us to be thinking about.
Yeah, I think Jitu had a question, yeah.
Oh, sorry. Go
when
ahead.
we talk about the charge, square of charge is equal to mass. You also said about plus or minus when we
Plus or minus square root of mass.
Yes.
Yeah.
Then does it imply an imaginary mass, something like in the
No, not to my understanding. Just like electric charge has two signs, but there's nothing imaginary about it. So plus minus E and plus minus square root of M. Square root of M is real.
Oh, okay. Okay.
Square root of M is real, but it
I
has...
thought the square, the minus sign is inside the square.
No,
I mean,
no.
square root.
That would not be nice.
Okay, sorry.
I think we probably do have to wrap it up now,
Yes.
Tejinder, if that's okay with you, unless there was something else you wanted to.
So thanks to everybody.
Yes.
Also done. Yeah, we can say bye now.
Well, thanks to everybody,
Bye.
especially us, not just our speaker, but in fact everybody. This has been an exceptionally rich and fruitful meeting, I think.
Yeah.